Fill up the polynomial, part 2. In part 1, we already figured out where Philip increased and decreased. Now we're going to figure out where this polynomial is going to be concave up and concave down. If you'll remember, finding out whether something is concave up or concave down will depend on us finding the second derivative. In the first part, we already found out that the first derivative was 4x cubed minus 12x squared plus 8x. We used the power rule to figure out the second derivative is 12x squared minus 24x plus 8. Now to a bit of a challenging part, finding the critical points of our first derivative. If you remember, we originally found the critical points of our function. That's where the first derivative is equal to 0 or does not exist. Here we're finding the critical points of our first derivative where our second derivative is equal to 0 or does not exist. This is a bit challenging because, as you'll notice, the factoring doesn't work out as quite as nicely as we want. F double prime was 12x squared minus 24x plus 8, which we're going to set equal to 0. When we do that, we can factor out a 4 and end up with 3x squared minus 6x plus 2. This does not factor easily. We can always resort, however, to our quadratic formula. When we do that, we end up with x is equal to 6 plus or minus square root of 36 minus 4 times 2 times 3 all over 6. Negative b plus or minus the square root of b squared minus 4ac over 2a. We can reduce this down. When we reduce it down, we're going to get square root of 12, which is the same as 2 root 3. And we end up with 1 plus or minus root 3 over 3 as our two critical points. Now, without a calculator, you need to make sure that you use some tricks on how to do a sign test on this. Our two critical points, as you remember, are 1 minus root 3 over 3 and 1 plus root 3 over 3. Root 3 over 3 is a number that's less than 1 but bigger than 0. Okay, so when we do 1 minus a number that's less than 1 but bigger than 0, that's still going to be a number that's bigger than x is equal to 0. So we can plug x is equal to 0 into our second derivative to test. When we do so, we're going to get a 4 times 2, which is a positive number. It should be obvious that the number x is equal to 1 is between 1 minus root 3 over 3, a positive number, and 1 plus root 3 over 3. When we plug in x is equal to 1, we're going to end up with 3 minus 6 plus 2, which is a negative number here, times a positive, which will give us a negative here. And at x is equal to 2, for the same reason that x is equal to 0 is less than 1 minus root 3 over 3, x is equal to 2 is bigger than 1 plus root 3 over 3, because root 3 over 3 is a number that's smaller than 1. When we test that, we're going to get 3 times 2 squared minus 6 times 2 plus 2, which is 2, which is a positive number. It should make sense that our signs alternate for the reason that all of our multiplicities on our roots are 1, or singular. Okay, when we have odd multiplicity, we're going to change signs around each of the roots. Below each of these, I drew a little diagram explaining what the derivative positive means. It means that we're going to have a concave up function, which looks a little something like this, up like a cup. At x is equal to 1, we're going to have a little concave down portion, down like a frown, and then up like a cup here. At x is equal to, or bigger than 1 plus root 3 over 3, excuse me. Therefore, f is concave up from negative infinity to 1 minus root 3 over 3, union with 1 plus root 3 over 3 to infinity because f double prime is bigger than 0, and f is concave down from 1 minus root 3 over 3 to 1 plus root 3 over 3 because f double prime is less than 0.